Well, hello and welcome YouTube. Mr. Robinson here, back with another video. A lot of material, not a lot of time. Let's go ahead and get straight to it. I have measuring, segments, and angles. I'm going to start with segments entirely and then go straight to angles afterward. Let's see if we can piece this all together. The good news is what we're doing with segments ties exactly in with angles. It's just a different visual, but kind of after you get the setup's kind of the same too. And after that, the rest is just algebra the rest of the way. Let's see what this looks like. I'm going to start by going over something called the segment addition postulate. Later here you see the angle addition postulate. You can already see a tie in there. And then midpoints. I'm not going to get into what are called segment bisectors really, but you can use those as well. And then there are angle bisectors, and they're kind of all one the same. Here we go. So before I dive into everything here, I just want to point out this word ray here. I think it's going to show up with the angle bisectors or just in different places. A ray is kind of the blend between a line and a segment where it has a single endpoint and then it extends infinitely in a single direction. Where you see this ray PQ, or you're going to see this thing PQ with like an arrow above it, only a single arrow in one direction, as opposed to a segment having no arrows and a line having two arrows. The ray shows the endpoint P as the first letter there, and then the arrow going through Q like that. Just wanted to call that out. I'm going to show you a whole slide on naming angles, though, after this. Okay, first let's start with the segment addition postulate, or abbreviated SAP, or I guess you can abbreviate it like that. It says the sum of the length of two or more segments that share collinear endpoints equals the length of the entire segment. All that means is if this whole segment here, AD, is kind of a straight line, and I say line in just a straight idea, not that it goes on forever, then I can add individual lengths of this, like the length of AB plus the length of BC plus the length of CD equals the length of the entire thing, all because they all go across a straight line. That's what kind of collinear means here. They all fall on the same line. If it bent like this, for example, no, this length plus this length does not equal, say, that length right there. But because they fall on the same line, we do that. So if A, B, C, and D are collinear, then I can come up with some statements here. I could say something like the length of AB plus the length of BC equals the length of AC. Or the length of BC plus the length of CD equals the length of BD. Or the whole thing, like I said before, the length of AB plus the length of BC plus the length of CD equals the length of AD entirely. And that's what the postulate states. And if you don't know what a postulate means, it's basically something that we have to accept as truth. There's nothing that we need to prove for it necessarily. It just kind of is truth, and we take it as it is. There's a logical reasoning behind it, and I think most of you guys can understand that. So let's take a look at some two examples here. Here I have measures of the length of KL is x minus 6, LM is 9, and MN is 2x minus 19. And the entire thing apparently is 23. Let's use this information to find the length of MK. Now MK is this segment right here. So I think what's going to help is if we find out what x is, then we can substitute x into here, add these two together, and I think we'll get our length. In fact, just really quickly, in a nutshell, guys, the length of MK itself is just taking the x minus 6 and adding 9 to it. So this one on its own can just be x plus 3. So when I solve for x, I can substitute it right into here. Okay, so let's go ahead and find the length of the entire thing. Let's find out if Kn is all of 23. Let's add x minus 6 with 9 with 2x minus 19 to get that 23. So here I can write x minus 6, well, how about, let's do that. X minus 6 plus 9 plus 2x minus 19 equals 23. Combine like terms, I get 3x, that's the x plus 2x. Negative 6 plus 9 was that 3. That's where I was going to kind of jump the gun. Minus 19 is negative 16. There. Add 16 to both sides and then divide both sides by 3. I'm going to get x equals 13. So I can take that 13 there and I can substitute it into here to solve for MK. That's going to be 13 plus 3, which is 16. So that is the length of MK in its entirety. Let me say that one more time. The length of MK equals 16. Now this is just one of many examples I'm going to do, guys, just in general. Segment addition postulate, just 2 examples. I do about 2 examples per thing, so I hope that it's okay that some time is taken just so you can learn it. All right, this one does not have a diagram, so I'm in that when in doubt, draw it out kind of camp. I think it's important that I do something along those lines here. Points A, B, and C are collinear. That means they all fall on the same line. It might be nice to even kind of just draw that segment to begin with here. B is between A and C. So here's A, here's C, B is somewhere in between. We don't know if it's in the middle or not. There's no assumption to be made. Just draw it and fill it out from there. AC is 3x plus 3. Now, although this diagram kind of showed this long strain right here, you'll often just see me do this, kind of that curly brace bit like that. This is going to all be 3x plus 3, the whole thing. AB is negative 1 plus 2x, so that's this right here, and BC is 11. Solve for AC and AB by finding x. So let's find x first. Let's add these two together. Once again, the segment addition postulate states that if I add the length of one portion with the other of collinear segments, they will add up to equal the whole thing. In this case, that's 3x plus 3. Combine like terms, negative 1 plus 11 is 10, so 2x plus 10 equals 3x plus 3. If I subtract 2x from both sides, I get x. Subtract 3 from both sides, I get 7. X equals 7 is a good start. And now, of course, I need to find the length of AC and AB. And we have pretty good expressions for both of those. So AC, the entire thing, would be 3 times 7 plus 3. 21 plus 3 is 24. And then, AB, you have a couple options here. I can substitute 7 into here, or I could subtract 11 from it because 11's one part of the piece of 24. I'm expecting 13 as an answer, basically, if I do this. So if I do AB by substituting in that 7, negative 1 plus 2 times 7, negative 1 plus 14, which is 13. So those are my two lengths there. That is the segment addition postulate in a nutshell, and we can check that one off the list. So add things together. Doesn't matter if it's 2 or 3, whatever. As long as they're collinear, you are set. All right, let's look at midpoints. Not on a graph. We're not averaging the value, so to speak. We're speaking more in terms of how the midpoints divide a segment. And it's very simple. The midpoint of a segment is the point that is exactly halfway between each of the segment's endpoints, dividing the segment into two congruent or equal parts. The word congruent means equal in size and shape. I'll be diving into that a lot more down the line. I'm just going to use the idea that the measures themselves are equal more so. You're going to see me put these tick marks here every so often, like right here and here. It's just basically a symbol that says this length and this length are the same. So if B is the midpoint of segment AC, then that does mean that the length of AB does indeed equal the length of BC. And one other thing that I can pinpoint into this is if it's exactly half, AB is half of this entire length here. So if AB is half of the length of all of AC, and so is BC, by the way, that also means that I could double AB and get that to equal AC. So you might see me use that concept there as well, depending on the problem. Now, there's also a thing called a segment bisector. I'm not going to get deep into it here, but a segment bisector is a line, ray, or segment that intersects a segment at its midpoint. So even if they didn't call it a midpoint, if there was a line that went through here and it said it bisected the segment, it basically divided the segment into two as well. We're not doing those here, but because we're going to do angle bisectors, I thought I'd throw it out there. Okay. So let's go ahead and take a look at some examples of midpoint. If B was the midpoint of segment AC, let's find the length of AC. We are given that, it's given that it's a midpoint. That means these two parts are congruent, which means that these two lengths will be equal in measure. The length of AB equals the length of BC. That means I can set these two things equal to each other. 2x plus 7 equals 5x minus 14. There's nothing that they're adding to that we know here, right? We're not saying this plus this equals something. We don't have that information, but we do know, we do know that they're equal. So if I subtract 2x from both sides here and add 14 to both sides, I'll get 3x equals 21. And then divide by 3, I get x equals 7. And now we need to find the length of AC. So we could, at this point now, we could say, hey, AC is going to be, substituting 7 into here, now we could add these, use the segment addition postulate, or we could take one length and double it. I'm just going to go ahead and add them together, hit home that segment addition postulate one more time. 2 times 7 plus 7 plus 5 times 7 minus 14. Now, whatever I get for 2 times 7 plus 7 will be the same as this, but here we go. 2 times 7 is 14 plus 7 is 21. 5 times 7 is 35 minus 14 is 21, right? So 21 plus 21. That's why I said we could double just one of them, and we get 42. That is the length of AC. There it is. So always answer the question, right? Just solving for x will not necessarily be enough. And like last time, there's no drawing for the second one here. M is the midpoint of segment PQ. Let's go ahead and draw a PQ of sorts and try and place M in the middle if you dare. M is right in that, didn't do it very well. M is right in the middle there. Midpoint of segment PQ, that does mean once again these two parts are congruent. PM is 5x plus 8 and PQ is 76. Be careful, I just said PQ, it's not this. Not this, PQ is the entire thing. So PQ is 76, this whole thing. Let's find the length of MQ here in a bit. Now these are congruent, so listen, you could write 5x plus 8 right here and you'd be good. We do have to make sure we're not going to set these equal to each other, 5x plus 8 equals 5x plus 8. We want to find a way to say that this, we can use this and this at the same time. And it's really about what I said before. If I double this length, if I double 5x plus 8, I will get all of that, which is 76. Or if I took half of 76, I would get 5x plus 8. That's kind of a good way to put it. You could do 5x plus 8 plus 5x plus 8, just giving you all the different options. Anyway, distribute 2 into here. We get 10x plus 16 equals 76. And work the rest of the algebra, of course. Subtract 16 from both sides and divide both sides by 10. We get x equals 6. Now find the length of MQ. Recall that MQ and PM are the same length. PM equals MQ, and we know that PM is 5x plus 8, so we can do 5 times 6 plus 8, which is 30 plus 8, which is 38. That will be the length of MQ. They are the same length because of the midpoint. And that's just the basic nutshell, guys. Just giving you an example of both of those, segment addition postulate and midpoint, and we can check both of those off the list. Angle addition postulate and angle bisectors will do the same exact thing, but just with angles. The one difference now we got to talk about is how angles are named and what they look like. So let's take a look at that slide next. Angles can be expressed with one unambiguous letter at its vertex. I'll get into what that means. 3 letters where the vertex is in the middle and a point on each arm, by arms I mean arms of the angle, as the first and last letters, or a signifier inside the arc. Okay, what does all of that mean here? First of all, the word unambiguous just means that you totally know what we're talking about with that one letter. Right here, I could call this angle, by the way, there's an angle symbol. It kind of looks like this in text. You're going to see me put an arc through it just to kind of make sure it doesn't look like a less than or something. I could call this thing here angle C. I can use a single letter to call this thing angle C because C is the vertex point, and it unambiguously is obvious that there is no other angle that I could be referring to when I talk about angle C. Clearly it's only this angle right here. However, if you have something like this, pretend like this A and B existed within this diagram here, I could not say angle C for, say, this angle right here because it is not obvious what angle C is in reference to. Angle C could have been this, it could have been this, it could have been this, it could have been this. There are a lot of other things that could have been angle C. So you can only use something like this if it's very unambiguous. That means very obvious what it is. I could have also called this thing angle 1. 1 is a signifier written inside the arc for that specific angle. And I am allowed to say also angle 1 over here. That is totally fine, once again, for this arc. And then the other one is the 3-letter one. And this is the most common one that you'll see because there are a lot of ones that are very ambiguous. You can't tell unless you state it with 3 letters. So the way that you do the 3-letter naming is you got to put the vertex letter in the middle, so say C, and then you got to use the letters that are points on the arms of your angle to make up your angle outside of it. So I could call this angle DCE or angle ECD. Those are your only other 2 options for that thing, and we can use that here one more time right here, DCE or EDC, if we were referring to that specific one right here. I just want to throw out the A and the B to say I could not call this angle C. You can call this angle 1 though. The 1 being inside the arc does make obvious. Anyway, those are different ways to name angles. Now, on these next pages, you're going to see something that says M angle something. Say it said M angle EDC. That's going to help tell you what the measure of the angle is. So let's say we knew that this thing was 40 degrees. We would say measure of angle, the EDC is 40 degrees. This one had nothing to do with the degrees. It was just another way to name it, to signify it. So you're going to see this here as well. Just like with segments, we don't have the bar above it, and that's when it means the length of. This just means the measure of, just to kind of hit it home. All right, let's go ahead and move forward because time will definitely be against me on this one. Okay, The angle addition postulate, much like the segment addition postulate, says I can add one segment with another to equal the whole thing. I can do the same thing with angles. The sum of the measures of two or more adjacent angles equals the measure of the entire angle. The word adjacent just means two angles that kind of neighbor each other. They share a common side right here. They share a common vertex. This angle right here and this angle right here, they're adjacent to each other. And as long as they are, I can add this measure with this measure to get the whole thing. So a way to write that statement could be the measure of angle ABD plus the measure of angle DBC. So this angle plus this angle measure equals the whole thing, equals measure of angle ABC. That's the basis of this thing, and that's what we're going to be doing for these problems. Let's go to them. Okay, the two examples. This one has no algebra, so to speak. Find the measure of angle WVU. Find the whole thing if the measure of angle ZVU equals 62 degrees. So here's ZVU. This is 62 degrees right there. And then this one, measure of angle WVZ, right here, WVZ is 50 degrees. Let's find the measure of the whole thing, WVU. Well, the measure of angle WVU is going to be the addition of those two. 50 degrees plus 62 degrees, which is going to be 112 degrees. That's how the angle addition postulate works. It is pretty straightforward, just like the segment addition postulate. Excuse me. And we'll continue that. Here we go. Find the value of x given that the measure of angle PQS equals 112 degrees. So the whole thing is 112. It's kind of harder for them to kind of label that. I'll do it for you. But the whole thing is 112, and it's the addition of the 10x and the 72. So here we go. We're going to say that 10x plus 72 equals 112 degrees there. Subtract 72 and divide both sides by 10. You'll get x equals 4. And that is the solution to that thing. That's all that they asked for. Just find x for that. So the angle addition postulate, much like the segment addition postulate, just add some things together, set them equal to the whole thing, and you're good to go. And the last thing to look at after we covered angle addition postulate are angle bisectors. Kind of like the midpoint of midpoints, of angles, if you will, just like how segment bisectors could have been a thing. Let's take a look at this thing. An angle bisector is a line, segment, or ray that intersects with the vertex of an angle equidistantly from its sides, dividing the angle into two congruent or equal parts. What does that mean? If you have this original angle, say right here, this ABC, if you have this angle ABC, and there's something that goes in the middle, like, excuse me, I'm just going to cut right through. It's a bisector if every point on this is exactly the same distance away from both of these, which means it's dividing it into two congruent parts. This part right here and this part right here are both equal in measure to each other. That's what it's saying. Just like it's like a midpoint, like I said, dividing a segment into two congruent parts, but now the bisector divides the angle into two congruent parts. So if ray BD is the bisector of angle ABC, then guess what? This is equal to this. So I'll go ahead and say, what is that? The measure of angle ABD equals the measure of angle DBC. So here's ABD, there's that angle right there, and here's DBC, that angle right there. So those two are equal in measure because of the bisector. All right, let's go ahead. Two more examples, and then I'm done. All right, here we go. The measure of angle DEF equals, oh shoot, I didn't change the letters. In fact, I didn't change the letters with this thing. Hang on, let me write this really quickly. My bad. The measure of angle ABX equals 5x degrees. That's embarrassing. So that thing is 5x right here. And the measure of angle, I'm sorry, this is XBC. See, I changed the letters in ABC right here. My bad. XBC equals 3x plus 10 degrees. That's that one right there. Find the measure of angle ABC. Okay, so just like the segment bisector thing, I don't know information about the whole thing in any sort of way, algebraic expression or nothing like that, but I do know based on the information. They didn't say it was a bisector, but they show these two angles are congruent. That does mean this is a bisector, by the way. So 5x equals 3x plus 10. I will make that equation to solve for x. Subtract 3x from both sides. I get 2x equals 10. divide by 2, I get x equals 5. Now, finding the measure of angle ABC requires, now that I add both of these things together, see, if I use the concept of the angle addition postulate, the measure of angle ABC does indeed equal adding these two things together, 5x plus 3x plus 10. So that becomes 8x plus 10 as a whole. And now that I know what x is, being 5, I can now say that this is 8 times 5. 8 times 5 plus 10, which is 40, plus 10, which is 50 degrees right there. So solving for x lets me substitute that thing in now that I use kind of the angle addition postulate to add those two together. Or substituting it in for one of these angles and then doubling that measure in the end. Right? That's something we talked about for segments. All right, and last example here, number 2, ray EF bisects angle DEG. This one does not have a drawing, so we have to figure out what the heck that thing means. If I have some angle DEG, and what that thing, oh my gosh, that is terrible. And what that means is, right here, maybe D is on one end, E is the vertex because it's the middle point, and G sits on another side. I have a ray EF that's bisecting it, which does mean, again, it's dividing this into two congruent parts. Single arc marks are indicating that right there. If the measure of angle DEF equals 3x plus 1 degrees right there, and the measure of angle DEG, that's the whole thing, guys, not FEG, but DEG, the whole thing is 5x plus 19, find the value of x. So this is kind of like the segment bisector thing. If this is 3x plus 1, then so is this. So if I double up the 3x plus 1, I do get the whole thing, 5x plus 19. And that's exactly what I'm going to be writing as an equation here. 3x plus 1 doubled, or plus 3x plus 1, equals 5x plus 19. And let's go to town on this guy here. 2 times 3x is 6x. 2 times 1 is 2, so 6x plus 2 equals 5x plus 19. Subtract 5x from both sides, I get x. Subtract 2 from both sides, I get 17. X equals 17. There's a good answer. Is that all we wanted? Yes, find the value of x. And of course, you can plug things in later if you need to. That's it. Okay, guys, that is covering everything here. I know I went super fast. I tried to get this under a certain time. Didn't hit under 20. Apologies, but of course the explanation goes through. Everything kind of holds one the same, but now you learned about naming angles as well on top of all these things here. So that ought to do it for me, guys. I hope that you learned something here. You can rewind if I went a little too fast there, but go ahead, take care.